What is the organic chemistry? Organic, until mid-1800s, referred to compounds from living sources. Mineral sources were inorganic. Wohler in 1828 showed that urea, an organic compound, could be made from a non-living source. Today, organic compounds are those based on carbon structures. And organic chemistry studies their structures and reactions. Includes biological molecules, drugs, solvents, dyes, food additives, pesticides, and others. Does not include metal carbonate salts and other simple ionic compounds. Carbon with hydrogen, nitrogen, oxygen, halogens, phosphorus, silicon, and sulfur. What is the atomic structure? You can see here structure of an atom. Positively charged nucleus, very dense, containing protons and neutrons, and small, 10 to the power minus 15 meter. Negatively charged electrons are in a cloud, 10 to the power minus 10 meter, around nucleus. Diameter is about 2 times 10 to the power minus 10 meter. What's about the atomic number and the mass number? The atomic number, Z, is the number of protons in the atom's nucleus. The mass number, A, is the number of protons plus neutrons. All the atoms of a given element have the same atomic number. Isotopes are atoms of the same element, that have different numbers of neutrons and therefore different mass numbers. Carbon has 2 stable isotopes. Natural abundance, 12 carbon, 98.89%, 13 carbon, 1.11%. The atomic mass, atomic weight, of an element is the weighted average mass in atomic mass units, AMU, of an element's naturally occurring isotopes. Atomic orbitals describe where an electron is likely to be found in an atom. Molecular orbitals perform the same role in molecules. Quantum mechanics describes electron energies and locations by a wave equation. Wave function is a solution of the wave equation. Each wave function describes an orbital, psi. A plot of psi square describes the probability of finding the electron. The electron cloud has no specific boundary, so we show the most probable volume. The boundary is called a probability surface. Shapes of atomic orbitals for electrons. For the existing elements, there are 4 different kinds of orbitals for electrons based on those derived for a hydrogen atom. Denoted S, P, D, and F. S and P orbitals most important in organic chemistry. Carbon atoms have no D or F orbitals. Look at the picture. S orbitals, spherical, nucleus at center. P orbitals, dumbbell-shaped, nucleus at middle. Orbitals and shells. Orbitals are grouped in shells of increasing size and energy. As shells increase in size, they contain larger numbers and kinds of orbitals. Each orbital can be occupied by 2 electrons, Pauli exclusion principle. First shell contains 1 s orbital, denoted 1s, holds only 2 electrons. Second shell contains 1 s orbital, 2s, and 3 p orbitals, 2p, 8 electrons. Third shell contains an s orbital, 3s, 3p orbitals, 3p, and 5d orbitals, 3d, 18 electrons. P orbitals. In each shell there are 3 perpendicular p orbitals, px, py, and pz, of equal energy. Lobes of a p orbital are separated by region of 0 electron density, a node. Electron configurations. Ground state electron configuration of an atom lists orbitals, occupied by its electrons. 1. Lowest energy orbitals fill first, 1s, to 2s, to 2p, to 3s, to 3p, to 4s, to 3d. 2. Electron spin can have only two orientations, up and down. Only two electrons can occupy an orbital, and they must be of opposite spin, to have unique wave equations. 3. If two or more empty orbitals of equal energy are available, electrons occupy each with spins parallel, until all orbitals have one electron. You can see here the ground state electron configuration of hydrogen, 1s1, carbon, 1s2, 2s2, 2p2, phosphorus, 1s2, 2s2, 2p6, 3s2, 3p3. Now we're talking about the development of chemical bonding theory. Kekule and Couper independently observed that carbon always has 4 bonds. Van Hoff and Labelle proposed that the 4 bonds of carbon have specific spatial directions. Atoms surround carbon as corners of a tetrahedron. You can see here 2 carbon-hydrogen bonds in plane of page, 1 carbon-hydrogen bond receding into page, 1 carbon-hydrogen bond coming out of plane. Now we talk about covalent bonds. Atoms form bonds, because the compound that results is more stable than the separate atoms. Ionic bonds in salts form as a result of electron transfers. Organic compounds contain covalent bonds, from sharing electrons. Lewis structures show valence electrons of an atom as dots. Hydrogen has 1 dot, representing its 1s electron. Carbon has 4 dots, 2s2, 2p2. A stable molecule results when the valence shell is completed. Octet, 8 dots, for second period main group atoms. And 2 for hydrogen. Number of covalent bonds to an atom. Atoms with 1, 2, or 3 valence electrons form 1, 2, or 3 bonds. Atoms with 4 or more valence electrons form as many bonds as they need electrons to fill the s and p levels of their valence shells to reach a stable octet. For hydrogen atom, 1 bond. For carbon atom, 4 bonds. For nitrogen atom, 3 bonds. For oxygen atom, 2 bonds. For halogen, 1 bond. Valences of carbon. Carbon has 4 valence electrons, 2s2, 2p2, forming 4 bonds, CH4. Oxygen has 6 valence electrons, 2s2, 2p4, but forms 2 bonds, H2O. Valences of nitrogen. Nitrogen has 5 valence electrons, 2s2, 2p3, but forms only 3 bonds, NH3. What are the non-bonding electrons? Valence electrons not used in bonding are called non-bonding electrons, or lone pair electrons. Nitrogen atom in ammonia shares 6 valence electrons in 3 covalent bonds, the remaining 2 valence electrons are a non-bonding lone pair. You can see here Lewis and Kekule structures of water, ammonia, methane, and methanol. Oxygen atom has 2 non-bonding lone pair. Nitrogen atom has 1 non-bonding lone pair. Carbon atom has no non-bonding lone pair. Valence bond theory. A covalent bond forms when two atoms approach each other closely, so that a singly occupied orbital on one atom overlaps a singly occupied orbital on the other atom. Electrons are paired in the overlapping orbitals and are attracted to nuclei of both atoms. H bond results from the overlap of two singly occupied hydrogen 1s orbitals. H bond is cylindrically symmetrical, sigma bond. In the diagram of the formation of hydrogen molecule from two hydrogen atom, reaction releases 436 kilojoules per mole. Product has 436 kilojoules per mole less energy than two atoms. That means H has bond strength of 436 kilojoules per mole. Bond length. Distance between nucleus that leads to maximum stability. If too close, they repel because both are positively charged. If too far apart, bonding is weak. The energy diagram on the right is called a Morse diagram. An atomic orbital represents the region of space, where one or two electrons of an isolated atom are likely to be found. A molecular orbital, MO, represents the region of space, where one or two electrons of a molecule are likely to be found. When atomic orbitals combine to form molecular orbitals, the number of molecular orbitals that result always equals the number of atomic orbitals that combine. Covalent bonds. A bonding molecular orbital results when two orbitals of the same phase overlap. An antibonding molecular orbital results when two orbitals of opposite phase overlap. Molecular orbitals in the hydrogen molecule. Two 1s orbitals combine together to form one sigma anti-bonding MO, and one sigma bonding MO, which is filled 2 electrons. Molecular orbitals in ethylene. The pi bonding MO is from combining p orbital lobes with the same algebraic sign. The pi antibonding MO is from combining lobes with opposite signs. Only bonding MO is occupied. Now we talk about the hybridization. Hybridization happens when atomic orbitals mix to form a new atomic orbital. The new orbital can hold the same total number of electrons as the old ones. The properties and energy of the new, hybridized orbital are an average of the original unhybridized orbitals. In their ground state, carbon atoms naturally have electron configuration, 1s2, 2s2, 2p2. In the excited state, one electron from 2s orbital move to 2p orbital. In CH4, all C, H bonds are identical. 1s orbital and 3p orbitals combine to form 4 equivalent, unsymmetrical, tetrahedral sp3 hybrid orbitals. They have the same shape and energy, they repel each other equally, and give sp3 hybridized carbon in CH4, its highly symmetrical tetrahedral shape. The 4 sp3 orbitals around the C atom point toward the vertices of a regular tetrahedron, and the ideal bond angles are 109.5 degrees. Tetrahedral structure of methane. sp3 orbitals on C overlap with 1s orbitals on 4H atom, to form 4 identical CH bonds. Each CH bond has a strength of 438 kJ per mole, and length of 110 pm. Bond angle, each HCH is 109.5 degrees, the tetrahedral angle. The structure of ethane. 2 Cs bond to each other, by sigma overlap of an sp3 orbital from each. Three sp3 orbitals on each C, overlap with H1s orbitals to form 6 CH bonds. CH bond strength in ethane is 420 kJ per mole. CC bond is 154 pm long, and strength is 376 kJ per mole. All bond angles of ethane are tetrahedral. sp2 orbitals and the structure of ethylene. 2 s orbital combines with 2 2p orbitals, giving 3 sp2 hybrid orbitals. sp2 orbitals are in a plane with 120 degrees angles. Remaining p orbital is perpendicular to the plane. Two sp2 hybridized orbitals overlap to form a sigma bond. P orbitals overlap side to side to formation a pi bond. sp2, sp2 sigma bond and 2p pi bond result in sharing 4 electrons and formation of cc double bond. Electrons in the s bond are centered between nuclei. Electrons in the pi bond occupy regions are on either side of a line between nuclei. When carbon atoms make use of sp2 hybrid orbitals for sigma bonding, the 3 bonds lie on the same plane. One such compound is ethene, in which both carbon atoms make use of sp2 hybrid orbitals. One of the remaining p orbitals for each carbon overlap to form a pi bond. A pi bond consists of 2 parts where bonding electrons are supposed to be located. H atoms form sigma bonds with 4 sp2 orbitals. HCH and HCC bond angles of about 120 degrees. CC double bond in ethylene shorter and stronger than single bond in ethane. Ethylene CC double bond length 133 pm, CC single bond 154 pm. sp orbitals and the structure of acetylene. CC triple bond sharing 6 electrons. Carbon 2s orbital hybridizes with a single p orbital giving 2 sp hybrids, 2 p orbitals remain unchanged. Sp orbitals are linear, 180 degrees apart on x-axis. 2p orbitals are perpendicular on the y-axis and the z-axis. Two sp hybrid orbitals from each C form sp sigma bond. Pz orbitals from each C form a pz pi bond by sideways overlap and pi orbitals overlap similarly. Carbon-carbon triple bond in acetylene, 120 pm, is shorter than carbon-carbon double bond in ethylene, 134 pm, and carbon-carbon single bond in ethane, 154 pm. Hybridization of nitrogen, oxygen, phosphorus, and sulfur. N's orbitals hybridize to form 4 sp3 orbitals. One sp3 orbital is occupied by 2 non-bonding electrons, and 3 sp3 orbitals have 1 electron each, forming bonds to H. Hybridization of oxygen in methanol. The oxygen atom is sp3 hybridized. Oxygen has 6 valence shell electrons but forms only 2 covalent bonds, leaving 2 lone pairs. Phosphorus can have expanded octets because it is in the n=3 row. Typically, phosphorus forms 5 covalent bonds. In biological molecules, phosphorus is usually found in organophosphates. Organophosphates are made up of a phosphorus atoms bonded to 4 oxygens, with one of the oxygens also bonded to a carbon. In methyl phosphate, the phosphorus is sp3 hybridized and the OPO bond angle varying from 110 to 112 degrees. In biological system, sulfur is typically found in molecules called thiols or sulfides. In a thiol, the sulfur atom is condensed to 1 hydrogens and 1 carbon and is analogous to an alcohol. In a sulfide, the sulfur is bonded to 2 carbons. In both cases the sulfur is sp3 hybridized and the bond angles are much less than the typical 109.5 degrees. Drawing chemical structures. Structural formulas indicate the way in which the atoms are attached to each other, and are not representations of the actual shapes of the molecule. Condensed structural formulas. Condensed structural formulas are somewhat faster to write than formulas and, when we become familiar with them, they will impart all the information that is contained in the structure. The efficiencies of drawing bond line formulas come from the fact that no CS are written for carbon atoms, and generally no HS are shown for hydrogen atoms, unless they are needed to give a three-dimensional perspective to the molecule. Three-dimensional formulas. Bonds that project upward out of the plane of the paper are indicated by a solid wedge. Those that lie behind the plane are indicated with a dashed wedge. Those bonds that lie in the plane of the page are indicated by a line.